If I asked you, which container in C++ are you most familiar with? I bet most people would answer vector. Indeed, vector is used so often that it appears in almost every project. Many people even think, isn't it just a dynamic array? Use it as is what's there to say. But today I'm going to pour some cold water on that. Vector might be the most misused container in C++. Not because it's difficult, but precisely because it's so handy and intuitive that we often overlook its critical underlying logic. Today, let's truly understand its underlying mechanics and avoid the pitfalls hidden in our code. First, we need to understand what the underlying structure of vector really looks like. This is the foundation for understanding everything. Actually, vector's underlying structure is extremely simple, relying on three core members. The first is a data pointer, which points to the start of a contiguous block of memory. All the elements we store live in this block, and we can get this pointer using data function. The second is size, which is the number of elements currently stored in the vector, obtained via size function. This is the used space. The third is capacity, which represents how many elements the entire contiguous block can hold, obtained via capacity function. This is the total available space. Here's an analogy to help you understand. Capacity is like the total area of a warehouse you rented, which can hold 100 boxes. Size is the number of boxes you actually have in the warehouse right now, say 30. The remaining 70 empty slots are the buffer space that vector has pre-allocated. When size is less than capacity, adding an element to the end is like placing a box in an empty spot. It's cheap and direct. But once size equals capacity, trying to add another element triggers a major operation, which is the root of many problems. With this structural foundation, let's define vector in one sentence. Vector equals a contiguous block of memory plus a set of automatic resizing management policies. Contiguous memory is vector's greatest advantage, bar none. First, it's cache-friendly. When the CPU prefetches data, contiguous memory allows it to load more relevant data at once, making traversal very fast. Second, random access is fast. one-time complexity. Accessing elements via the array form is essentially calculating addresses from the data pointer with no extra overhead. This excellent memory locality is also why vector is favored in scenarios demanding extreme speed, such as game engines and high-performance computing. But every advantage comes with a cost. The problem lies in the automatic resizing management policy. Many people only know that vector can grow automatically, but completely underestimate the cost of resizing and overlook the chain reactions it triggers. Next, let's break down the three most common pitfalls of vector one by one. First, look at this piece of code everyone has probably written. Very simple. Loop 10 times and push back elements into a vector. I'll put the code on screen. This code has no issues. It compiles, runs, and outputs the correct result. But have you ever wondered, are these 10 pushback operations really just about placing elements at the end? Actually, no. This is vector's resizing logic. When size equals capacity, the warehouse is full. It doesn't just add one more slot. Instead, it rents a larger new warehouse, usually twice the size of the old one. Compilers may vary slightly. Then it copies or moves all the boxes, old data, from the old warehouse to the new one, and finally releases the old warehouse. This process is called reallocation. What's more critical is that the moment reallocation occurs, everything related to the vector's elements that you previously obtained becomes invalid. This includes pointers to elements, references to elements, and iterators. There are no warnings, no exceptions, and the compiler won't hint at it. The program may seem fine, but has already planted a time bomb of undefined behavior. Now, let me show you another piece of code that's very common in real projects. Many people write it thinking it's fine. This code might run in debug mode and even produce seemingly correct results. But I must tell you, this code is extremely dangerous. The problem lies in the pushback line. If this pushback triggers a reallocation, the iterator used in the loop immediately becomes a dangling iterator, pointing to old memory that's already been freed. Any subsequent iterator increment or dereferencing becomes undefined behavior. The scariest part is that this kind of bug is latent. It might work fine in testing, but only surface in production under high concurrency or with large datasets. The reason is simple. Iterators are essentially wrappers around the data pointer. After reallocation, the data pointer points to new memory, but the old iterator still points to the old memory, making it invalid. The third pitfall is something many people overlook. We've probably written code like this to remove the first element. Semantically, this code is intuitive. Delete the first element. But from an underlying perspective, its cost might far exceed your expectations. As mentioned, vector uses contiguous memory and must maintain that contiguity. After deleting the first element, all subsequent elements must shift forward by one position to fill the gap. If the vector contains 1 million elements, deleting the first element means moving 999,999 elements. This operation is ON, not the intuitive O1. If this line of code is on a hot path, like a game's frame update loop, or a high-frequency data processing logic, it can directly cause a performance crash, making the program unbearably slow. Here's a performance test code you can run yourself. Use a vector with 1 million elements and delete the first element, then measure the time. After running it, you'll find that this seemingly simple erase is orders of magnitude slower than popback at the end. Popback is 01. It just removes the last element without moving anything. At this point, you might think, so is vector just bad? On the contrary, vector is one of the highest performance containers in C++, provided you use it in the right scenarios. What are the right scenarios? First, read heavy, write light. Most operations are traversal and element access, with few insertions, deletions, or structural changes to the container. Second, appending or deleting elements only at the end. Pushback and popback are both O1 operations with no memory movement, extremely efficient. Third, predictable data size. If you can estimate how many elements you'll store, you can pre-reserve capacity to avoid reallocation. Fourth, requiring extreme traversal performance. The cache friendliness of contiguous memory is something non-contiguous containers like list or map can't match. Traversal is simply faster. This is why game engines, high-performance computing frameworks, and various low-level libraries heavily use vector. They use vector where it fits best, leveraging its strengths. Conversely, avoid using vector in these scenarios. Frequent insertion or deletion at the head or middle of the container. Completely unpredictable data size with no chance to pre-reserve. Frequently modifying container size during traversal, pushback while iterating. In these cases, list or deck might be more appropriate. Based on the above analysis, here are 4 actionable engineering recommendations to avoid vector's pitfalls at the root. First recommendation, and the most critical: pre-reserve capacity. This isn't just an optional performance optimization, it's a key practice to avoid reallocation disasters. If you know roughly how many elements you'll store, use reserve to allocate memory upfront. For example, if you know you'll store 1,000 elements, call reserve 1,000 first. Then pushback won't trigger reallocation, and pointers or iterators won't become invalid. Second recommendation, separate traversal and modification. Don't modify the vector structure while traversing it, pushback or erase during iteration. The correct approach is to collect what needs to be modified first, then apply changes after traversal. For example, if you need to append elements while iterating, store them in a temporary vector first, then use insert to add them all at once after the loop. This avoids iterator invalidation at the root. Third recommendation, avoid frequent erase. Use the erase remove idiom instead. If you need to delete multiple elements, don't erase them one by one. Each erase moves memory, which is inefficient. Use the erase combined with remove if pattern, the erase remove idiom, to move memory only once, which is much more efficient. For example, to delete all even numbers, you can do it in one line efficiently. Fourth recommendation, use indices instead of iterators when necessary. If you absolutely must modify the vector while traversing it and have already reserved capacity, use index-based access instead of iterators. Indices calculate addresses directly, and as long as you've pre-reserved, there's no reallocation, so indices won't become invalid. These 4 recommendations cover most engineering scenarios. Keeping them in mind when using vector will help you avoid most pitfalls. So, vector itself isn't flawed. It's one of the best designed containers in the C++ standard library. The real issue is, it's so easy to use that we forget its underlying behavior, forgetting about reallocation, iterator invalidation, and the true cost of erase. Only by understanding these can you truly use vector effectively, not just use it. That's all for today. I hope that from now on you'll use vector safely and efficiently, avoiding its pitfalls. See you next time.